what we had stopped off with last time was working through standard multiple regression, okay? And with this model, I want you to be very clear on exactly what's going on with these different approaches to regression. Here we're taking all of our predictors, all of our IVs, and pushing these into the model at the same time, okay? So again, as we talked about coefficients in just a standard, you hear this simultaneous multiple regression. These coefficients are just looking at their unique relation between your individual predictors and your outcome, okay? Because, and again, we touched on this last week, because in psychological science, our predictors are often correlated, sometimes pretty strongly correlated. We can get situations where we can have individual predictors that have quite large bivariate correlation with my outcome, but come up as not statistically significant within the context of my regression model. Sam, why might we see a situation like this?
Because the other IPs in the model are stepping out or very...
Yeah, right. X1 and X2 are basically measuring the same thing. They're completely overlapping. Anything that X1 relates to has a relation with X or with Y, X2 does as well. And so even though X1 and X2 both individually might have very strong correlations with outcome, when we put them both in the same model, all that goes away. So this is why it starts to become important when we're thinking about putting a regression model. And clinical folks, if you want to drop a BDI score in there, that's just negative affect, and that's just going to suck up all sorts of variability with everything, right? So I want to be careful with that. Same thing, experimental folks, right? I want to throw neuroticism in a regression model. If you're looking at other negative stuff, right, that's just going to suck up a lot of that variance, and you might swamp out effects that you're actually looking for, okay? So again, wanting to look at both your bivariate correlations and your regression coefficients when you're looking at this model, so you get a sense for what type of overlap is going on, what the impact of that is on your outcome, okay? And so with the simultaneous regression, what we're doing is we're looking for the unique contribution of individual predictors once we account for other variables in the model, okay? Questions about simultaneous regression, kind of what the idea is or what we're working towards with this? Okay, so what I want to do, we'll save ourselves some time because we got through most of this last time. We'll just work through this is pretty big, but that's all right. Okay, taking a look at our regression output here. So this is what we started working through last week in our design. So what we were going through, we're looking at a model here where we're predicting with, again, these are data that are pulled from car accident survivors from the community who are struggling with some anxiety-related stuff. And what we want to do is see to what extent severity of pain, right? Physical pain, opiate use, and PTSD are uniquely related to overall role functioning, right? And so we went through, we screened these, went through, took a look at opiate use here, and we're finding that opiate use pretty balanced, right? We got 201 people in the sample, 101 people are not taking opiates, 100 are, right? And so we've got a pretty balanced sample here. That's not always going to be the case with your dichotomous predictors. Keep that in mind because it's going to become relevant when we get into centering and some of these things. But in this case, we've got pretty even opiate use here. And then we're going down through and we're looking at our descriptive statistics. Alex, what do we see in our descriptive statistics that made us do a double take and sort of make a mark on the checklist? What's that?
Okay, you asked what.
So for our screening for our descriptives here, what did we key in on with this?
Kurtosis is high for role functioning.
Yeah, so for role functioning, we've got a good level of skew, good level of kurtosis. At this point, when you're saying that, you should probably already have a pretty good sense for what that histogram is looking like, right? Remember, skew kurtosis less than 2 is within our bounds, but skew kurtosis of 2 doesn't mean that that graph is going to look normal. That distribution is actually going to look probably pretty nasty, right? And so when we go through and we examine our box and whisker plots here, this is what we get, right? PTSD total is pretty good here. We're liking that all right. Pain severity, I mean, it's not as pretty as this, but overall we're not too worried. It looks like we've got a little bit of a negative skew there. But then when we break down and take a look at our role function variable, Morgan, what did we recognize? So our role function variable scale is 0 to 100. But when we jumped into this, what did we find? What did we notice or realize with this role functioning scale?
The majority of participants were 0.
Right, so nearly everybody's 0. What about the measurement properties of the scale? Is this a truly continuous scale? 0 to 100, right? That seems continuous. What did we find when we actually looked at the data?
Were they actually categorical?
It's actually, it's ordered categorical functionally, right? There's not an infinite number. It's not 100 possible values or 101 possible values. It's actually 5 values, right? 0, 25, 50, 75, and 100, right? And so again, and this is the thing that ends up starting to become very problematic as we move forward, and continues to be throughout this whole example. We've selected an outcome variable that has pretty poor measurement properties, at least within this sample. Now, maybe if we weren't working with a sample, healthy seeking sample, if we were just looking at this in university participant or university undergraduates, we'll probably see, well, no, we're probably going to see still a negative skew, because most people are going to, most people are probably going to be pretty good, and we're going to have a negative skew going on there. But within this sample, right, these are people who've been involved in major car accidents. We're having enough continuing difficulties to come in and sign up for assistance through a research clinic at a university. These are all people who are reporting chronic pain as a function of their accidents. And so we've got pretty low levels of functioning almost completely across the board, right? And so looking at this, this is starting to raise flags, say, this is probably something that we want to do something with. Now we've got 200 people in the sample. This gives us a little bit of cushion, right? But this distribution is probably going to start giving us fits down the road. So one thing that you might want to do, even when you see a box and whisker plot like this, well, Lauren, why does this box and whisker plot look this way?
Because the majority of participants resort to 0.
Yeah, and not just the majority. What does this tell us about characteristics of?
Everyone endorses 0 except for the ones that are over like 100%.
Yeah. So based on this, what is the median? Yeah. What's the 25th value of the 25th percentile? What's the value of the 75th percentile, right? And so that's we got one line, right? And so we are identifying this as something that we should probably do something to try and address. And so we didn't do this in the example, but what we kind of proceeded on and said, okay, well, what would happen if, right? But in actual fact, if this was my own data, if I were doing this, I would probably want to say right off the bat, I should probably think about trying to transform this, right? And we'll talk about in just a moment. For a positive skew, one of the nice things, or an advantageous transform to use is a natural log function, okay? And natural log function will oftentimes help us to some extent with, or will help us with a positively skewed value. And so what I'm going to do is I'm going to tell SPSS to compute, roll the natural log, and I'm going to set that as equal to the natural log of my roll function variable plus 1. Right? Katie, why did I say roll functioning plus 1?
Because you can see the natural log.
All right, so 1 is now my low value, but I can take the natural log of 1, right? And so I'm going to go through and create a new variable here. So I have the natural log of roll functioning. Now, one thing to recognize, right? If I have 4 values in my raw variable, or 5 values in my raw variable, right? And then I take the natural log and I transform this transform this variable, take the natural log of it. Okay, how many values am I gonna have in my transform variable? 5, right? It's not gonna spread things out, right? It's not gonna create additional values in there. I'm still only working with, at the end of the day, transform doesn't fix the fact that I'm working with a categorical variable functionally, right? But what it hopefully will do is go through and start to, at least from my skew and kurtosis perspective, try and start to make this look maybe a little bit better, right? So I go through, run my transform here, and then go through and get descriptive statistics on my natural log. And Sam, what do we see once I look at the descriptive statistics for the natural log of roll functioning?
And that becomes better,
Yeah, improved considerably, right? My kurtosis went from 4 something to 0.2. My skew went from 2.3 down to 1.4, 1.5, right? So at least in terms of the distributional characteristics, if I'm looking at the 3rd and 4th population moment, it's been improved. Do my histograms look all that improved? No, right? We've brought things in, right? And this is what this transform is going to do. It's going to bring things in closer, so things aren't strung all the way out. Our logs, our natural log transforms are going to bring that tail in, so it's a little bit better. But at the end of the day, this is a nasty looking distribution. There's nothing that we can do to this distribution. I mean, we might play around with different transforms and we might get marginally increased values of skew and kurtosis, right? But nothing is going to turn this into a nice distribution, right? And so at this point, what I would probably say is, okay, this is probably good enough, right? I've used a transform that has advantageous interpretive properties. I could play around with additional transforms, but the transform variable, at least within values of skew and kurtosis, is within bounds. I might find a transform that drives that down a little bit more, but at the end of the day, that's probably not worth my time, and it's not probably going to have a huge impact on my outcome, and then I would lose interpretive value of the natural log transform, so I'm just going to stick with this, okay? So go down through, take a look at my descriptive statistics, my z-scores here. Alex, what am I looking for in this table? Outliers. Yeah. Do we see anything here, any extreme values that would cause me pause? Not really, right? We've got a large sample. We've got 200 some people in here. It's large by our standards, right? We're expecting to have some people out on the end of the distribution, and so we're probably saying, okay, with that log transform in particular, we've made some progress on that. So now we're going to go down through, request some correlations and plots. Stephanie, what am I looking for with my correlation table here?
Linearity and consistency.
Okay, well, with my graphs, right, what about my correlations? What am I looking at here?
Multilinearity.
Yeah, looking for some linearity stuff, right? And if we're looking at here, things look all right, right? These are about the level at which, again, if you remember back to your effect sizes, these are moderate correlations, right? We've got a large correlation between pain severity and the natural log of roll functioning, okay? Remember that anytime you transform a variable, it's no longer what you started with, it's a different thing, right? So we can't just pretend that we didn't do that and interpret it as roll functioning. This is the natural log of our roll functioning as measured through this scale, but nothing here that's going to, I mean, we might make note of the relation between my predictor and my outcome, right? But that's not necessarily a bad thing, right? If I have a predictor that has a strong relation with my outcome, right? Looking at correlations between my three predictors, they're actually not too bad, right? So this is a semi-efficient, a more efficient regression model than probably some that you'll run into at some point in time, right? And so then going through, taking a look, remember to get this graph is kind of slick to look at these all together. In the multivariate, general multivariate screening, we went through the procedures for having SPSS produce something like this. Any concerns that we see, Stephanie, here in terms of linearity, heteroscedasticity? Not too bad, right? Certainly not in terms of linearity, right? There's no nonlinear, obvious nonlinear relations going on here. We might make an argument to see some evidence of heteroscedasticity in relations with the natural log of roll functioning here. But again, it doesn't, like, this isn't a 3-to-1 difference where we would say, okay, this is extreme. And both of these that are looking like they're having a little bit of a fan are involving our variable that has a nasty distribution to begin with, right? We don't have that many values out here. So again, not great, but it's something that we could probably tolerate, at least from this perspective. Yeah?
Am I just going over how to interpret the fanning one more time?
Interpret the what?
How to like look at the fanning one more time? The
heteroscedasticity. Again, yeah, what we're looking at, remember we're looking at something that here, the idea is that when we're looking at a linear relation between two variables, that we want for our assumption of multivariate normalities would say that for every unit of x, we have equal variability in y, right? And so generally, if we get something that looks a little bit like, so we got pain severity and PTSD total right here. This is a better representation of something that much more better approximates continuous variables, right? So you kind of have this cloud. And so if I were to catch any value of pain severity, variability in PTSD scores are about the same, right? Pretty close, right? Now if I look at, say, the relation between PTSD and roll functioning, however, looks like we got, and again, this makes this a little more clear because this isn't actually continuous. It's just 5 variables, and so these variances are all lining up along each one of these, right? And so I can see if by the time I get to my highest level of roll functioning, it looks like the variability here is about half of what it is here, right? And so what we would start to probably note is potential it looks as though there's evidence of heteroscedasticity here, right? Now, this graph doesn't suggest that it's big enough to probably invalidate our analyses, but it's certainly looking like as roll functioning increases, people's level of PTSD is decreasing. Yeah.
Is there a rule of thumb for how many values should be in the line to be able to count that as like a range to compare it throughout?
Yeah, it's not a rule. I mean, this is again, thinking about your data, right? And this is why large samples are advantageous to small samples, because the larger my sample, the more likelihood is I'm going to get people representing the full range of my X variable, right? And for any value of X, I'm going to have a number, for any value of X, I'm going to have a number of cases, and they're going to have a number of values. In any of these, right, what's our big violation that we started out with that we almost always violate anytime we're running a regression analysis? Angela? What was assumption number 1? Not normality. Something we hardly ever talk about. Anybody recall?
Follow a normal distribution.
No.
No, oh, sorry, predictor variables. It's non-random, measured without error.
Right, non-random is measured without error, right? Now, if, well, our role function is our outcome variable, so this would be a fixed, we don't assume that our outcome is a fixed variable. We assume that our predictors are fixed variables. But if role function was a predictor in our model, right, what we would do is we would say, all right, we're going to get 25 people with values of 0. We're going to get 25 people with values of 25, 50, 75, 100, and we're going to systematically sample. So we have people representing each one of all possible values. So with this scale, right, for any possible replication that could ever be done with the role functioning scale of the SF36, there's only 5 values that people can take. What we've done is systematically made sure that everybody, we have representation for every single one of those values. That would be a fixed variable approach for this if it was one of our predictors, right? But we don't do that, right? If we're looking at pain, we didn't go through and make sure that we have like individual representation of every possible value on the caps and every possible value on the pain scale. We just had people come in and whatever they got, right? And so these are random variables, right? And we can see here, you know, this is a nice example of, I mean, now we've got, it's not a completely scatter, I mean, you see kind of lines here, right? But when we're looking at this, what we're looking at is wanting to see, and it's just an extension of our assumption of homogeneity variance with ANOVA, right? It's just instead of 1, 2, 3 groups that we're testing and assuming that equal population variance across all those 3 groups, we're just extending the groups out to an infinite number of groups and saying for all possible values of this predictor, treating each one of those as its own population or its own group, and assuming that corresponding variability in whatever our outcome is going to be identical for each one of those. Okay. Yeah, the heteroscedasticity, and this is kind of a difficult thing, kind of, but once it clicks, it'll make some sense. All right, so here, not too worried about stuff, although we'd probably note that some evidence of heteroscedastic relation where we see reductions in variability of PTSD total with increasing values of the natural log of role functioning. But we're going to say this is about, for these data, this is about the best that we can do. So we're going to go down through here, run our analysis, okay? And when we do this, Katie, help me out. What are we seeing here in this first box? And what does that tell us? So some things, now remember that be careful with shared variance, right? Because your R squared, it's the variability that's common across those and also their unique variability. So it's all the variability, right? And so what we would say right, is that based on our regression model, we estimate that the best linear combination of pain severity, opiate use, and PTSD total is accounting for about 38% of the variability in the natural log of growth function. Okay? And so this is our multiple correlation here. This is our R squared, so we interpret it as a proportion of variability. Our adjusted R squared, this is the adjustment that we would make based on the number of variables and how collinear they are and things along those lines. This is arguably a better population estimate of proportion of variability accounted for. As we talked about, we don't probably worry about adjusted R squared as much as we would here versus business or finance or something where we're actually trying to, like, the goal was prediction, like the actual original goal of regression, where what we're trying to do is maximize proportion of variability in our outcome. I also did some digging, found out standard error of the estimate. This is a standard deviation of your residuals. Okay, so if you go down through and you were to take the mean square, your mean squared residual, right? So this is mean squared residual is the variance of your residuals, right? So how far you're off. Your standard error of your estimate is just the standard deviation of your residuals, right? So if you take the square root of your mean squared error, you get your standard error of your estimate here. So if we think about how far are we off from our predicted value, you can quite literally think about this as, on average, I would expect an observed value to be about 1.3 units away from the actual predicted value. Right? So if you were interested in very literally wanting to know how much, so here's my predicted values, right? How far am I going to be off within the units of your natural, or within units of the natural log of roll functioning, we're expecting 1.3 on average, 1.3 units on your natural log of roll functioning scale in terms of difference, average difference between your predicted value and your outcome. Okay. So that's what that is. So it's not actually a standard error for these because that doesn't make sense. All right, Angeline, tell me about this ANOVA table. What are we looking at the ANOVA table?
You're seeing that it is different from 0.
Mm-hmm. What is different than 0?
So regression.
Yeah. What value is different than 0? What's this a test of? Of the regression model, yeah. And so we have a statistically significant model, but what is this a specific test of?
Natural log of function.
Not natural log of roll functioning. R squared, right? So this is a test of whether or not this value is reliably different than 0. Okay. This is what this whole ANOVA table is taking a look at, right? Saying, are we, basically what the ANOVA table here is asking is, does the best linear combination of these predictors account for some non-zero proportion of variability in my outcome? Okay. It doesn't tell us, it's not a good metric of how much, right? Because what can I do to make sure that this is a statistically significant model? Yeah, just jack up my number of people in my sample, right? I have 50,000 people in my sample. I could throw whatever random nonsense into this model I'd like. And so this is probably going to be something that's technically not 0, right? But this is what we're doing. Again, and recall that values in terms of our sum of squares regression, sum of squares residual, sum of squares total, these map onto are kind of analogous to the same types of things that we were talking about with our ANOVA models, right? Sum of squares total, This is just the sum of the squared deviations of each individual each person's role functioning value from the mean, right? So if here's the mean, here's where everybody's values are. So that this is just the total variability in my outcome, right? My sum of squares regression is the sum of the squared deviations, deviation from the predicted value from the mean, right, of y. Because if I have no predictors that are in any way related to y, and I say, what's Angeline's a participant in my study, and I say, what's Angeline's predicted value for outcome, what do I guess? What do you think, Sam? Well, I've got IVs. IVs just aren't related to what I'm trying to predict. What's my best guess for Angeline's value? What's my predicted value for Angeline? The mean outcome, right? Because if I've got, my predictors are hair color and favorite movie song and, I don't know, other random things that don't relate anything to anything, my best guess for Angeline's outcome value is just the mean for the sample, right? So our sum of squares regression is the sum of the squared differences between my predicted value for every person and the mean value, right? So what does our regression model give us above and beyond just predicting the mean for everybody, right? And then sum of squares residual, what is the sum of squares residual? Anybody remember? Is going to be the sum of squared deviations between your predicted values and your observed values. Right? So again, recall that slide where we've got, here's the mean y, right? Here's my regression line, and then there's my data, right? What we're looking at here for our sum of squares total, squared deviations of every individual observation from the average value of y, right? Sum of squares regression, the deviation, sum of squared deviations between my mean value of y and my predicted value for each one of these individuals. Sum of squares error, or my sum of squares residual, going to be the sum of the squared deviations between predicted values and each one of these individual points. Right. So again, thinking about these in terms of practical, sort of conceptually, what this is. Right. Sum of squares total. Right. Total variability in my outcome. Right. Total variability in my y. Sum of squares regression. What we're getting above and beyond just predicting the mean with my regression line. Sum of the squared deviations from the mean of y to my predicted value for each person in the sample, and then my sum of squares residual being the sum of the squared deviation between the predicted value and the actual observed. And if we put this all together, same way that we did in ANOVA, we get an F value that tests our R squared value, and in this case, it's statistically significant. Questions about that? Yeah.
So we're mainly interested in the R squared value, and with significant values, that's kind of your own value.
It depends on who you ask. I don't get too worked up about it, right? I mean, it's problematic if you have a regression model and you don't have a statistically significant model, because you can have significant coefficients. You have coefficients that are statistically significant and an overall model that's not, right? And so then it starts to become tricky, like, well, we didn't actually get my regression model isn't statistically significant, but individual predictors are registering as reliable, and then it's kind of a tricky place to be in, right? And so, in general, right, I mean, it's good to report your R squared and that you do have a statistically significant model. you'll generally have significant models, particularly in psychology, where everything's related to everything, right? But this is what we're looking at here. Also, other thing too, right? Remember that as our R-square goes up, what does that do to the standard errors for our individual predictors? Drives them down, right? If I'm not predicting a whole lot of variability in my outcome, it makes my standard errors for my individual regression coefficients bigger, right? So the better my model is, right, the better chances is that it's a well-specified model, right? Because remember, one of our assumptions is that we have a well-specified model, or correctly specified model, and if my regression model accounts for all of 2% of the variability in my outcome, I probably don't have a well-specified model. I probably have a crappy specified model. And who knows what that's going to do to my estimates. They're going to be biased all over the place, right? As I start to account for more variability in my outcome, I begin to create a more powerful test of my individual coefficients, right? So it's advantageous to think about what goes in here. Now think carefully, right? You don't want to just dump in 50 predictors to try and drive up that R-squared. But from a power standpoint, if I have variables that are uniquely predicting a greater proportion of variability and they're not all stacked on top of one another, it's increasing, it's going to help, all things being held equal, probably help with driving down and reducing my standard errors. So jumping down into my coefficients table here, okay? Morgan, tell me what we're getting here with this regression constant. What is that telling us?
The intercept where it crosses y.
Mm-hmm.
So it's crossing y at 4 when x is 0.
Okay. When what x is 0?
When
All x's are 0, right? And again, when you're thinking about this, anytime you're struggling with regression, think about literally what does this mean, right? And your math is going to be helpful with this. Like, draw out your regression equation, right? And it's very quickly, you see very quickly, if I plug 0 into all these x variables, what I'm going to be left with is this, right? And so here, we're seeing that my expected value of role functioning, when pain severity is at 0, when opiate use is at 0, what does this mean if opiate use is at 0? No one's using, right? So what I would say, right, is for people who aren't using opiates, who register pain scores of 0 and PTSD scores of 0, I would expect their role functioning value to be 4.3. Or the natural log of their role functioning to be 4.3. What about, and we get a statistical test of this, and what does that mean with my constant is statistically significant, Morgan? It just means that value is not 0, right? So again, not terribly interesting like 99% of the time, but just wanting you to know kind of what that is. When you start to get into higher linear modeling and some more advanced types of regression stuff, sometimes this does become relevant. For us in our typical day-to-day basic regression stuff, it doesn't, but wanting you to know what this means and what it corresponds to. What about, Morgan, my pain severity coefficient here, what does that tell me? Are you joking me? I'm sorry, I got really hostile. On edge, my nerves are frayed with technology in this university. So, all right, what does that coefficient tell me?
The magnitude of the slope of the line, so it's a negative slope.
So it's a negative slope, and so give me a practical interpretation of this.
With 1 unit increase in pain severity score, we'd expect a 0.68 unit decrease in natural role function.
Perfect. Okay. Only thing I might add to that is, and again, we'll see that this isn't a huge issue, but one thing to keep in your mind is that controlling for other variables in the model. We're holding other variables in the model constant at 0. Okay. with these additive models, that's actually not a big deal, but when we get into our moderation stuff, it will be, right? So holding opiate use and PTSD total respond to a 0.69 reduction in the natural log of rural functioning. What about, and so again, if we think about what that means, right, we can say those words, but essentially it's saying for someone who's not taking opiates, who has a PTSD score of 0, I would expect a 1-point increase in pain severity to correspond to a 0.69 point reduction in the natural log of rural functioning. Okay. What about, and this is statistically significant, right? And we have our effect sizes down here. We have we've requested confidence intervals for this coefficient. We have our correlations here. We've got our bivariate correlation. We've got our partial correlation. Can someone tell me what partial correlation, remind me what that means? If I square that partial correlation, what does that give me? Remember 70?
Not particular.
How about this? What about the semi-partial correlation? If we square that, what does that tell me?
I don't remember specifically, but I remember we were discussing about like the movement versus shared.
Right.
I just can't remember.
Okay, so remember that what we're working with here is always working with what's going on with the denominator, right? So our part is our semi-partial correlation, right? And if we square that semi-partial correlation, this is going to tell me the unique proportion of variability in the natural log of rural functioning, or the proportion of variability in the natural log of rural functioning that's unique to pain severity score. Okay, so the proportion of the total of all the variability in the natural log of rural functioning. So we've got a correlation 0.56 or 526. If I 526, if I square that, so that gives me 0.27, 0.28, right? And so what I can interpret this as saying, I could say that pain severity accounts for about 20, or it accounts for, it starts to have some causal language, but we'll ignore that for right now. So pain severity accounts for about 28% of the, uniquely accounts for about 28% of the variability in the natural log of rural functioning, right? Controlling for opiate use and PTSD total. So your semi-partial correlation and your standardized coefficient, very similar, right? Both of these are looking at the unique relation between your predictor and your outcome. Denominator just switches around a little bit. You can't square this and make an interpretation of it, but you can square your semi-partial correlation and say that in this case, again, about 28% of the variability in, we would estimate that about 28% of the variability in the natural log of rural functioning is uniquely attributable to pain severity score controlling for opiate use and PTSD. Now, with that refresher, what's the interpretation of our partial coefficient, or our partial correlation? Can you remember, Lauren? So if our semi-partial, if our squared semi-partial is telling us the proportion of the total pie that's attributable, uniquely attributable to a predictor, what does the partial correlation give us?
With the outcome.
What's that?
With the outcome.
Mm-hmm.
So
So remember, here's this, here's this, here's this, right? What's up? Exactly, right? And so what we're looking at with our squared partial correlation, this is the proportion of residual variability in the natural log of rule functioning that's unique to, or that's attributable to whatever the predictor is, right? So if I go through and I take 0.556 and I square that, I get a value of point, so my partial squared is 0.26, oops, 0.277, and my partial correlation squared is 0.309, okay? Well, my semi-partial correlation is telling me is that pain severity score uniquely accounts for about 28% of the total variability in the natural log of role functioning, controlling for opiate use and PTSD. Right? What my squared partial correlation is saying is that pain severity accounts for about 31% of the residual variability in the natural log of role functioning after we section out opiate use and PTSD total. Okay, this is what's left over. Over. There we go. Right. What we're saying here is the piece of the pie that we're accounting for here starts to be different, right? So we're still talking about, if this is pain and this is natural log of roll, right? Numerator of both of these coefficients is this piece right here, right? This ends up being the same, right? But what we're dividing this by to get this proportion is this versus the total thing, which corresponds to which coefficient? The semi-partial. And if we're just taking about this proportion here relative to that, what's that looking at? That's the partial, right? Because we're saying, all right, this piece of the variability, that's been accounted for by pain and whatever variables we have in the model. So we're just going to suck that out, right? And so what's going to have the smaller denominator? Our semi-partial or our partial? Partial is going to have the smaller denominator, right? Because we're talking about that in terms of residual variability. Now, this starts to become difficult to conceptualize because I don't know, based on that partial correlation, how much variability in my outcome has been accounted for. It could be a lot, it could be a little, right? But the nice thing to recall about our partial correlations is that these follow standard metrics of effect size, where we can say this is small, this is medium, this is large. It starts to make it more, if you're wanting in a paper to provide effect sizes for your coefficients, just give a partial correlation, don't square it, just give it your partial correlation. That's a nice measure of it. This is a massive effect, okay? Now, the nice thing about your semi-partial correlation, this is a nice intuitive interpretation, right? We're saying that pain severity is accounting for about 28, uniquely accounting for 28% of the variability in our outcome controlling for opiate use and PTSD, right? So that has more of an intuitive meaning. That's kind of nice too. So depending on your purpose, you might decide which one of those two things you want to do. But just need to remember that if we're talking about our partial coefficient, or if we're talking about our partial correlation, this is, and we square that, we're talking about the proportion of the residual variability attributable to an outcome controlling for other variables in the model. We're talking about our squared semi-partial correlation. This is the proportion of variability uniquely attributable to this controlling for other variables in the model. Right? So again, this is it'll click and it'll slip away from you. You just want to make sure that you're strong on these interpretations. So interpretations are your part and parcel correlations. All right. So jumping down through, we've got an effect for opiate use. Okay. And so what is, Katie? What would be my interpretation for this coefficient for opiate use?
Would expect a 1 unit increase in the opiate use corresponding to 0.09 increase in natural law.
Okay. What does it mean if we have a 1 unit increase in opiate use? They are used, right? And so what is this functionally, what is this coefficient functionally equivalent to? What could we think of it as similar to? Okay, so again, can you tell me what it means if we have a 1 unit increase in opiate use?
There's a 0.029 decrease in the natural law.
Okay, but conceptually, what does it mean if we have a 1 unit increase in opiate use? Yeah, we've gone from someone who doesn't use to someone who does use. And there's a decrease. So functionally, what does this end up being similar to? An idea? Kind of like a t-test, right? Again, recall that you could run a t-test in a regression environment. All you have to do is take your dichotomous variable and regress it onto whatever, right? Basically, this is saying we're expecting a 0.039 difference between people who do take opiates and those who don't, right? That's all it means if we're going from this group to that group. It's just a mean difference, right? Now, this coefficient isn't statistically reliable, so we can't say that there's a difference at all, right? But you can think about this as kind of like an ANCOVA model, right? So if we adjust for pain and PTSD, this is the average difference in our outcome that we would expect between this group and that group, okay? So again, thinking about t-test is just a special case of linear regression. Same exact thing, right? So when you've got a dichotomous predictor like this, you can look at this unstandardized coefficient as your expected mean difference between this group and that group controlling for other stuff in the model. Right now, it's not a straightforward mean difference assumption because basically we've made adjustments, right? It's a difference in adjusted means here, but functionally that's what we're doing with this dichotomous predictor here. And then the same thing for PTSD total. We're expecting for every unit increase in PTSD total score, we're expecting a 0.01 unit reduction in the natural log of world functioning. Now this is a really small number, but it's still statistically significant, right? A lot smaller than this one, but it's still statistically reliable. What's going on? Why is this so tiny and still statistically reliable? What do you think, Alex? What was our PTSD scale? Do you remember? What's that?
0 to 136.
Yeah, 0 to 136. And what about that pain scale?
0 to 6.
Right. So we've got a much finer, a much more fine-scaled, a 1 point increase on a 0 to 136 scale is minute, right? And so even though this is small, it's still statistically reliable. Here, we've got the 7-point scale, and so those jumps are much larger, right? And so when we're looking at our unstandardized coefficients, very hard to determine just based on the unstandardized coefficient which one of these is small or larger than the other relative to, unless all of our predictors are on the same exact scale, right? And so, Stephanie, what could we look at within a regression model to start saying, okay, this is the relative magnitude or strength of these individual predictors? Yeah, our standardized coefficients, right? And can you tell me, give me an interpretation of this standardized coefficient here?
For every standard deviation increase in PTSD total score, there is a corresponding negative 0.162 standard deviation unit decrease
fantastic. Couldn't have said it better myself. It's a mouthful, right? And you'll never see in an actual research paper someone describe it that way. But I want you all to internalize this in your head. So when you abbreviate it short, like there's that sort of memory traces back there, so you know exactly what it is. Because when we start getting into moderation and more complex types of regression analyses, these types of things are very, very important to keep in mind. Okay, so we've got our t-tests. These are 1 degree of freedom tests, right? So we can actually reproduce this. If I take a look at a t-test, a t-value, a test statistic of negative 0.202 with 200 degrees of freedom, I'm going to get a p-value of 0.840, right? I've got our confidence intervals here, which are nice correlations, and then collinearity diagnostics. I didn't see any problems here, Lauren, with collinearity within these 3 predictors. Now, how do I know that?
Tolerance, it just has to be greater than 0.1.
Yeah, technically you're right, but like you should be very concerned. If it's 0.4, 0.5, it suggests a lot of overlap here. And why? What's the utility of these versus just eyeballing your bivariate correlations? So we could have 2 variables, or we could have a set of 3 variables that were all unrelated to one another, only weakly related to one another. But if we put all 3 of those together in multivariate space, a combination of 1 and 2 might be collinear with a 3rd, right? And we can't identify that in just a bivariate correlation table, right? And so if variable 1 is subscale 1, variable 2 is subscale 2, and then variable 3 is the product of those 2 things, now all of a sudden we have a singularity in there, right? Because if I know what the value is for x1 and the value is for x2, I know exactly what the value for x3 is, right? So even though x1 and x2 might be correlated 0 with one another, when we throw that 3rd one in there, then everything gets mixed up. And so that's why we want to go through and make sure that, unbeknownst to us, we haven't included variables that end up some combination of x1, 2, and 4 aren't perfectly reproducing x5 or something like that. Okay. So people feeling good about identifying this, interpreting things, and understanding what all this means? Yeah.
So going back to the unstandardized coefficients, so the unit that's being described here would be based on the scaling?
Yep.
Okay, so it's literally like if I were on a 1 to 7 point scale, 1 point, 0.013 would be, I don't know, like significantly different from 0 or something.
Well, it depends on what's going on in multivariate space here, right? But let's say my predictor's on a 7-point scale, 1 to 7, right? This would say that, well, and so for pain severity, right? For if I were to jump from a score of 3 to 4, or I were to jump to a score from 5 to 6, right? That 1 unit increase, again, we're working with a linear function here, right? And so if I go 2, 3, 4, 6, 7, right? If I go from here to here, from here to here, or from here to here, right? It's the same increase, right? It's always the same increase because it's a line, right? And so this is just saying this is the amount of rise that we would expect per 1 unit of change, right? But if I'm not on a 1 to 7 scale, if I'm on a 1 to 136 scale, that's the unit I'm talking about, right? And so this is why on this scale, so my unstandardized coefficient is quite small, right? But on the aggregate, it's still corresponding to a pretty long line, right? So if I have, and we'll talk about this when we've got, when we get into scale, so I see that a 1 point increase or a unit increase in my predictor corresponds to like a 1/10 of an increase in an odd ratio, right? That's not super helpful. But if I were to say, well, 1 unit isn't a useful unit, but a standard deviation would be, or a 10-unit increase, right? I take this coefficient and multiply it by 10, and just say, for the 10-unit increase in my scale, I would expect a 0.13 increase in the natural log of rho function, right? So scaling, we can play around with that. That doesn't impact this at all in the additive model. Okay. So that's why it's hard to just look at an unstandardized coefficient and tell whether or not it's corresponding to a strong relation or a weak relation. It's kind of impossible to tell. So within the context of a single model, that's where we would go to our standardized coefficients and then say, okay, in this case, this is looking like a relatively small effect, right? But this is clearly a large effect here, right? So basically, your standardized coefficients would put everything on the same scale. Other questions? Okay, so we kind of jumped the gun on this because probably what we should have done first before we start making strong interpretations is take a look at our collinearity statistics, right? Those are all looking fine, and so we don't have to move down to our collinearity diagnostics. But if we go through and we take a look at our residual statistics here, remember we're working with a natural log of rho functioning. If we look at our standardized residuals, we're not seeing a standardized residual. Those are all below 3, right? So those are pretty good. If I look at my Mulholland-Otis distance, right? Mulholland-Otis distances for individual cases run from 1 to a little over 11. Recall that with these are distributed on a chi-square distribution with degrees of freedom equal to the number of predictors. So I got 3 predictors in this. Cut score critical value for chi-square 3 degrees of freedom at p equal to 0.00 or at alpha equal to 0.001 is going to be 16.26, right? So am I concerned about multivariate outliers in this group? No. Okay. But when I go through and I look at my residuals, remember that in my regression analyses, my primary concern is with my residuals and not with my observed variables, right? In terms of thinking about linearity, homoscedasticity, equality of variability, or equality of equal variance, right? Assumptions. My concern is making sure that these residuals are normally distributed, that I don't have nonlinearities in my residuals, and that I don't have heteroscedasticity in my residuals, right? Now, if I'm eyeballing things at the variable level, that should sort of cue me into potential issues going down the road, right? But at the end of the day, I might have bivariate relation to an x1 and y that looks heteroscedastic, but if I have another variable in my model, my residuals might look fine, right? Again, we talked about the relation between age and income, right? That's probably going to be heteroscedastic or heteroscedastic because as age increases, variability around income is going to increase, right? But we talked about if we account for education, that's going to account for a lot of that spread, right? And so in our regression model, if we're regressing age and education on income, our residuals might look fine despite at the bivariate level seeing heteroscedasticity there. So that's why we want to take a look at both of them, right? But when we look at our residual plot for this model, do we have concerns? Remember, this is a plot of predicted values against our standardized residuals. So think about these as z-scores, right? And what we want to do in a good pattern, we would draw a line here across at 0 and then just see a nice big cloud around around that midline. Is that what we're getting here? No, right? And to some extent, this is going back to the issue that our outcome variable here is not a continuous variable. It's an ordered categorical variable, which is why we're getting these weird lines here, right? But what about if I go through and I run a line, and again, I'll do that, I'll just draw a line just right here, or if I paste this into a Word document, just draw a line so I can take a look and see what's going on. What's our primary concern about these residuals? So again, remember, residuals, we're looking for normality, we're looking for homoscedasticity, and we're looking for linearity. Okay. You have problems with linearity? No? I'm not seeing anything that would look nonlinear here. What about normality? Do I have problems with normality here? Again, if I draw no? Okay. That's what?
On the other side.
Oh,
Yes.
look at that.
Beautiful. That's a
Okay.
question.
It's quite fast. But hang on it. Go away. All right. Am I seeing problems with normality in these residuals? Absolutely, right? We have skewed residuals here, right? So if I look for here, right, and here, like I'm not getting it's kind of here that like I'm getting incredibly skewed residuals with this, right? My residuals are not normally distributed in this outcome. And this is a direct consequence of me having a funky outcome variable, right? And so remember, if we go back through and we take a look at consequences of our violations, and this is starts to become important, consequence of violations of normality, well, we're concerned that this is going to shrink our standard errors. It's going to attenuate our standard errors if our residuals aren't normally distributed, right? And so what does that do, Lauren, if my standard errors are shrunk up? It inflates my test statistics, right? So I might find things are statistically significant, but I violated the basic assumptions of my test that under these conditions, I can trust the results of this test. I violated those conditions. It's still going to run the test for me. I'm just concerned that I'm going to be making too many type 1 errors in this situation. Okay. So here, violation of normality of my residuals is a big issue, right? And something that we would want to say, if we put our consulting hat on, like, hey, it's your life, I'm just living in it, but I can tell you what's going to go on with this stuff if you choose to proceed with this model. Okay? And then what about heteroscedasticity? Maybe, right? It's kind of got a weird thing going on, but I mean, we just don't have that many cases here or here. Looks like maybe more, but I mean, if we're looking at variability across my residuals, it's actually, yeah, it's actually not terrible until we get out here to where we've just got cases where we don't have a lot of variability, and then out here, I'm actually less worried about homoscedasticity in this case, because again, if we look at, oh yikes. Right? That's actually pretty cool, right? What actually is going on, like variability in my residuals actually isn't it's kind of this, it's fairly okay. It's got a weird thing where it's kind of stepping down, and then we get into this tail and that tail, where things kind of go around, right? And so I would be less concerned in this situation with, all right, how do I get rid of all this stuff?
It's tracked.
Oh, race right there. Right there, right there. Right above the pen. No, right above it. Right
Ah.
above it.
No, I did it. I did what I wanted to do. Okay. All right. Go away now.
It goes away by itself.
Okay. Can I erase this?
Oh, it's gonna start.
That's all right. That's all right. I'll just do that. Okay. So people see what's going on with this and how this is sort of what we would want to be looking at. And this is really a crappy residual plot to give it to you guys on your first run out because there's weird stuff going on there. But you are able to see kind of what we're looking for in this and how we would say, really in this case, it looks like our normality of our residuals is kind of the biggest situation here, probably more so than variability.
Is it more normal? What we see? Like, I'm having trouble understanding how we know that this is a distribution.
So in terms of skew, right, if we see everybody bunched up here, like 4, whatever this value is, huge cluster here, and then a couple up here, right? It's a skew, it's got an upward skew. Same thing here, upward skew, upward skew, upward skew, right? But the skew that we're seeing is a direct function of the fact that our outcome variable sucks, right? And probably shouldn't be something, we should probably choose a better outcome here. We won't because this is what it is, but this is kind of what's going on with that. Okay? So going down, so let's say that we had just run through and decided not to do anything and just regressed roll functioning onto our predictors. Like, what would the impact have been then? If we go through and we take a look at our model, R squared is about the same, right? We've still got a statistically significant model. We still have pain severity being statistically reliable. PTSD total also reliable, although our effect here is smaller than what it had been before, right? Or at least in terms of effect smaller. No, so coefficient is a little bit larger. Oh, that's about the same. It's comparable here, right? Collinearity doesn't look like as though it's that terrible. But if we go down through and we look at our residual statistics, we see, remember that we didn't have a standardized residual that was greater than 2 or greater than 3 in the previous model. Here, we got a standardized residual of working close to 4, right? If we look at our residual plot here, I mean, it's still got the same general type of shape, but we've got much more spread on some of these things. If we look at our Mulholland's distance is still about the same, right? So we can see, at least from our residual plot, that the previous one was bad. This one is probably a little bit worse, right? And so the corrective action that we took against just choosing a poor outcome variable, not that roll function is a poor outcome variable, but the way we measured it probably isn't great, right? At least within the context of this sample. So it was probably worth going through and trying to do some remediation on that to bring that skew in relative to what we would have had without it. It looks like it doesn't impact the overall story all that much, but from a statistical standpoint, just far more responsible to go through and address this, but recognizing based on the fact that we violated that normality assumption that this starts to degrade our confidence in some of our individual coefficients. All right, how are people feeling about this? Was this helpful to walk back through, make sure that we're feeling strong on all this stuff? Okay, cool. Jump back in. So this is our talking about understandable regression. One thing, remember, or kind of a factoid that's worth keeping in mind, that technically what we shouldn't be doing, if I've got paper one, if I've got Sam et al. 2017 and Lauren et al. 2018, they run pretty much the same model, but they've used different samples. And we want to say, you know, how comparable are their results. Probably shouldn't be reporting, comparing standardized coefficients, okay? When we compute our standardized coefficients, what we're doing is we're rescaling all of our variables to a mean of 0, standard deviation of 1, basically we're creating z-scores, and then running a regression with z-scores. And so what ends up happening is if Sam's sample is notably more variable in their scores than Lauren's, what we end up is we have coefficients that are measured on different metrics, right? Because standard deviation in Sam's study was 15 and it was 7 in Lauren's. And so now what we're doing is we're comparing apples and oranges here, right? So if you want to take a look at, you've got a comparable regression model across a couple of different papers, or you've run a regression model and then you've got a really big, say you got 500 people, be like, okay, what I'm going to do is I'm going to split this in half. That's actually probably not worse because you don't have completely different samples. But if you've got this sample here and this sample here in different analyses and want to compare standardized regression coefficients, don't. Go through, take a look at your unstandardized coefficients, because your unstandardized coefficients are on the same scale if you're using the same measures, right? So those are a better metric to compare across independent studies than your standardized coefficients, okay? But then this starts to become important when we think about reporting, right? Why might it be advantageous to report standardized coefficients? What do I get out of it? If I'm reading a paper and I look down, I see standardized coefficient, how is that helpful to me? Yes,
You have to know what, since it's standardized, everybody really knows what the next do.
yeah, it gives me a pretty good sense for the general idea of the strength of that unique relation between X and my outcome, controlling for other variables in the model, right? Standardized coefficients can exceed 1 sometimes, but I mean, it's not like a correlation where it's bounded by -1 and 1, but generally, right, if I see a standardized coefficient of 0.5, I know that's a pretty big standardized correlation, or a standardized effect, right? But if I want to do comparisons across models, and all I've done is report standardized coefficients, then I'm kind of out of luck, right? Because I don't know if it's something where the outcome is meaningful, and I want to know literally what a 1 unit increase in my predictor corresponds to an expected increase or decrease in my outcome. I don't have that, right? Or if I want to compare against studies, I don't have that unstandardized coefficient. So when we think about reporting our regression models, important to somewhere in the paper include both unstandardized and standardized regression coefficients, also the standard errors for your unstandardized coefficients, and then I would say also include some metric of effect size, whether it be partial correlations or squared semi-partial correlations, depending on how you want to present that. Sometimes our effects are quite small, and if we present squared semi-partial correlations, one, we don't have standard benchmarks for interpreting those. And if all your effect sizes are like 0.001 0.02. That's kind of sad to look at. Correlation might be a better way, because then you would say, oh, there's small effects based on the benchmarks type of thing. All right, so our standard regression model, this is what we went through. So questions being, do PTSD symptoms, pain severity, opiate use count for a significant portion of variance in role functioning among accident survivors? What was the answer to that question? Yep, right, it does, right? Best linear combination of PTSD, pain severity, and opiate use counts for reliable variability in my outcome, right? And again, about 38% based on R squared. And then what is the unique relation of PTSD, pain, and opiate use with role functioning following a motor vehicle accident? Well, looks like both PTSD and pain hold a unique relation with role functioning as our outcome. Opiate use didn't show up and having a reliable association there. If we go through, okay, if you look at your correlation table on that outcome, right, did we see that, does opiate use have a relation with the natural log of our role functioning variable? What do you think, Katie? Yeah, and what makes you say that we do have a relation to an opiate use role function? Yeah, right. So we do have a significant bivariate relation to an opiate use and role functioning. Looks like for people who's based on that correlation, who's doing worse? People who are on pain medications or who aren't? Yeah, people on pain medications are doing systematically worse in terms of role functioning. But once we account for shared variability with PTSD, and shared variability with pain, overall pain, opiate use no longer has it. There's nothing unique. There's nothing left over in terms of opiate use that holds a unique relation with our outcome once we account for pain and PTSD. And so then that drops off. And this is typically what we'll see when we start adding variables in, is we start to see that our regression coefficients, our standardized regression coefficients are often become smaller in the context of a multiple regression than would in the bivariate case, because as we're adding in overlapping predictors, this shared piece of that, right? So here's the overall variability I share with my outcome, but as I start to add other things in that overlap, that relation starts to get smaller and smaller. All right. Note on our natural log transform. So in this example, we actually did go through and use a natural log transform. Natural log is helpful for addressing the skewed distribution, and as I've said before, it's helpful because it has some advantageous interpretive properties. Depending on what we're transforming and where it's at in our model, it starts changing around our definition or our interpretation a little bit. So if I've transformed my outcome variable using a natural log, right, what we would interpret this as is a 1 unit change in X associated with percent change in Y. This is cool because it actually means something, right? So with this model that we just ran, if we're looking at our coefficient for opiate or for pain severity, we had a coefficient of -0.69. And we would say for every unit increase in pain severity score, we would expect a 69% decrease in role functioning, or a 69% decrease in role functioning is expected given a unit increase in pain severity, right? That's nice, it's intuitive, it's meaningful, right? And so that ends up being helpful. So if we transform our outcome variable, we're interpreting our unstandardized coefficient as a unit change in X is associated with a percentage increase or decrease in our outcome. On the other hand, if we have an independent variable, a predictor that we log transform, we're interpreting that coefficient as, not a unit change in x, but a 1% increase or decrease in x corresponding to some change in outcome, right? So let's say that we transform, say, the natural log of pain, right? And we get a point or negative 0.45 coefficient. We would say 1% increase in pain severity associated with a 0.45 decrease in role functioning. Also useful, right? Helpful there. If we transform both our log transform, we have a log transform predictor, log transform outcome, then we're talking about a 1% change in 1% change in x associated with a percent change in y. If we have not natural log of pain, natural log of role functioning, and we get this coefficient, we would say we would expect 1% unit or 1% increase in pain severity associated with a 2.77% decrease in role functioning, or vice versa. So depending on what type of combination you have with this natural log transform, this is just really nice because our main concern is that we lose interpretability with the transform. If we are able to incorporate natural log transform, it alleviates a lot of that concern. Questions? People see how this is all transforming and working together, stuff like that? Okay, excellent. Cool. So we've talked about our simultaneous multiple regression, right? Other type of regression we'll often see is a hierarchical regression. It's hierarchical regression, not goddamn magical regression, like most people would like to believe. Okay, hierarchical regression is useful in some cases, but it's not doing anything that's terribly different than what we're doing in our simultaneous regression. So what we're doing with our hierarchical or sequential regression is we're just entering predictors or set of predictors into the model at different stages. Think about this as just not running one multiple or simultaneous multiple regression. You're just running additional models that are just kind of building off of one another, okay? So with hierarchical models, we see a couple different strategies. One, what we can do is throw in the variables that we think are important into initial blocks to account for sort of whatever it is that we hope to account for, and then enter our control variables later on, just parcel out like nuisance stuff, right? So I want to see the relation between x1, x2, and x3 with my outcome, but then I've got x4 and x5 that I just want to go through and check out, right? So I go through, run 1, 2, and 3 in the first block, say, this is what's going on, these are the unique effects that I'm seeing, and then these hold once I throw in control for x4 and x5, okay? So the thing is, we're saying, all right, this is the effects that we're getting, and these effects remain the same even when we control for these other things. Or when we control for these other things, so we have 1 and 2 are demonstrating unique effects, but then when we throw in our controls, we actually lose that, and it's just x1 that it ends up being statistically reliable, okay? Other thing we can do is we can enter our control variables first, sort of suck out all the sort of nuisance variants that we're worried about, and then throw in our primary variables of interest in subsequent blocks to see if these additional variables are contributing predictive ability to the model above and beyond sort of just our basic stuff. So here, this might be a situation where, say, variables x1, 2, and 3 are all things that are known to be predictive of our outcome, right? This is well established. What we're interested in is 4 and 5. This is new stuff that someone hasn't actually taken a look at. We want to see whether or not these additional variables account for proportion of variability in my outcome above and beyond the stuff that we already know is going on, right? People see kind of the differences in these two approaches, right? Now the only difference, though, is what we get between these models is change in our R squared at each step, okay? So think about, in this case, right, we've got x1, 2, and 3 that we enter in the first step, right, because these are the things that we think are important. Then the second step, we add in a couple of control variables or nuisance variables or covariates, whatever we want to call them, and see if those individual predictors are still statistically significant. All we're doing here is in this first step, we run a simultaneous regression with our 3 predictors. And then the second step, we just run the same regression except with all 5 predictors. And the only thing that's different with that is we just look at the difference that we see in the R-squared statistic. Okay? The model that we run in the second step with all 5 predictors is the same model that we would just run. It's the exact same model that we would get if we would have run all 5 of those in the first place. Right? It's not that the first 3 get all the variance and then the other ones get what's left over. In that second step of the model, it's just the simultaneous regression we would have just run all 5 anyway. The only thing we get is a change in our R-squared value, right? So with 3 variables, we are accounting for 20% of the variability in our outcome. And with 5 variables, we're accounting for 25% of the variability. We see a 5% increase in our R-squared. Is that a statistically significant increase in our the total variability that we're accounting for? Okay. So again, only difference, the only thing we're getting in this hierarchical model is our change in R-squared each step. And so again, the actual regression coefficients that we're seeing are no different than the regression coefficients that we would get in just the simultaneous regression model. Okay? So I have fights with reviewers about like, oh, you did this incorrectly. This has to be run in a hierarchical regression. Like, no, it doesn't. It is the exact same thing. The only thing that you would get with that is if I were to add these models in, I can say this is how much this best linear combination of this set of variables accounts for. And if I add more of that, this is the proportion of variability this accounts for. I can calculate the difference between those two and say, yeah, it looks like the addition of these 2 additional variables improves the model as based on if we're looking at proportion of variability accounted for, but that's it. That's all these models do. Okay. People get this turned around with a sequential or statistical regression, but it's not. We're just stacking simultaneous regression models on top of one another. Okay. So for example, just to walk through an example of this, let's say we're going to run this in a hierarchical regression. We want to know what's the incremental contribution of pain severity to the prediction of functional outcome above and beyond medication use. What's the incremental contribution of PTSD to functional outcome above medication use and opiate use and pain severity. So if we take the same sort of variables that we used in our example, if we run our standard regression, right, this is what we get. We have our R-squared 0.367, right, this is what we just saw, right? So the combination of opiate use, PTSD, and pain is accounting for close to 38% of the variability in our outcome. This is what we would get with a hierarchical regression, right? And what we're doing is in the first block, we're including opiate use. In the second block, we're including pain. The third block, we're entering PTSD. Okay? So if we would run this in SPSS, this is what it's going to give us. It's going to say, for our model with just opiate use, we're accounting for about 5% of the variability. If we then go in and add pain severity, a model with pain severity and opiate use is accounting about 34% of the variability. And if we look at our R-squared change, that's an increase of about 30%. And if we go through and we take a look at that increase in 30% is obviously statistically significant, right? So we could say, yes, the inclusion of pain severity does add to or improve the model above and beyond just having opiate use as our predictor. Then if we go down here, we look at model 3. This is just saying that a model with opiate use, pain severity, and PTSD total accounts for about 38% of the variability in my outcome. I get the addition of PTSD adds about 3% of the variability in my outcome. It looks like that change, that 3% increase, also statistically significant. Okay. So, Morgan, what is this looking like here, this R-squared value? It's the same thing as up here, right? So all we've done is we just run 3 different models. We just ran this one, and then we ran this one, and then we ran this one. SPSS just kind of combined it up into a model for us. But this model is no different than this model that we would have just ran. Only thing that we're getting with this is this R² change at this point and at this point. If we take a look at our ANOVA table, here's our ANOVA table for our standard regression model, our sum of the squares, regression residual, our F, right? We're getting the same thing here. This is just our ANOVA table for just one predictor, right? And so opiate use is a significant predictor, right? We get a significant overall model. If we add in pain, right, that's also a significant model. If we add all 3 variables, that's a significant model, right? It's just, we could build this by just running one model with 1 predictor, second model with 2 predictors, and 3 models with 3 predictors, and just stacking these on top of one another, right? If we go through and take a look at our coefficients, same thing here, right? This is our coefficients table from our standard and simultaneous regression. Again, this is my regression, or my coefficients for just opiate use. This is a separate model where I add the 2 in together. This is the 3rd model where I end up having all 3. My coefficients in, Sam, what's the relation of my coefficients in step 3 of this model with my simultaneous model? They're identical, right? Because it's the same thing. The only thing that I get with these hierarchical models is just a change in my R². That's the only thing that's different, okay? So, if you're really hard up to get a change in R², and that's an important thing, then awesome, run a hierarchical model. If that's not what you're interested in, it's not necessary to go through and run things in a hierarchical model. I mean, it's window dressing, basically. Some people like be very excited about having sort of this different stuff, but you just, if all you're interested, if this is all you're interested in, is just really in this final model, just run the final model. It'd be less pace in the journal space that it'll take to run through all of this stuff. Okay. So again, you'll probably find at some point in your life people giving you pushback like, oh, this has to be done as a hierarchical regression model. Your hierarchical regression model isn't doing anything aside from just allowing you to calculate and test that increase in R² with the addition of additional predictors in there. Okay. Cool. All right. Stepwise regression. This is what people are getting confused with. Okay. Stepwise or statistical regression. What we do here. So our simultaneous regression. We say these are the predictors I'm interested in. Right. This is the set of 5 predictors that I'm going to take a look at, and I'm interested in the unique effect of these individual variables on my outcome. Okay. With a hierarchical regression, I say, okay, well, I'm going to take run these 2 in the first block, these other ones in the second block, and then I'm going to run the 3rd one in the 3rd block and see sort of what the relative contribution of the total model is with the addition of these variables. With the stepwise regression, what we do is we, like simultaneous regression, we dump everything in the hopper. But what ends up happening is we get differences in the estimation, depending on what type of, what version of this we're running, where what we do is we go through and we say, predictor with the strongest relation with my outcome, that gets all of that variability, okay? So all of the shared stuff that first variable has with my outcome here's my outcome, and let's say I've got this, okay? So x1, x2, x3, and that's my outcome, okay? And let's say x1 has the strongest bivariate relation with my outcome, okay? Now in a simultaneous regression, what proportion of variability would x1 get credit for? Just this piece, right? But in a stepwise regression, x1, because it goes in and has the strongest relation, gets all of that, okay? In a simultaneous regression, this would get put into this proportion of variability here, this space would get thrown in the R² value, but x1 and x2, neither x1 or x2 would get credit for that because it's overlapped, right? But in your stepwise regression, if X1 has the strongest correlation, overall correlation with your outcome, X1 gets all of this, right? And then what's left over, and so let's say that obviously X2 gets, has more, and so then X2 gets all of that. And then we get down to X3, and X3 now is just kind of hanging down there at the end, so X3 doesn't get anything included in. And so what ends up happening when we look at the coefficients for this stepwise regression, this is the coefficient for X1 is going to be larger than in a simultaneous regression because X1 is getting all of this stuff, right? And then X2 is getting all of what's left over that's related, and then X3 is kind of left leaving for scraps here, okay? And so if we have in this type of model, what often happens is you'll see I've got 50 predictors, and I'm just going to dump them all in there, right? And it's just a battle royale, fight to the finish, and see what variables are in there and what comes out as the best, as the most strongest predictors based on bivariate correlations. And if we have variables not meeting some threshold for entry or retention, those get kicked out, and those don't end up being included in the final model. Okay? So, what ends up happening though, conceptually, mathematically, these are controversial models that you probably won't ever have the occasion to use unless you're interested in doing some type of machine learning, at least within the context of the type of research that we do, right? The type of research that we do is often, or should be, theory-driven, right? I think that this is I'm including this predictor in the model because of this. There's a theoretical reason for me to believe that this should hold a relation with my outcome. It might not be very big, right? I'm testing mechanisms and things that are on the margin, but based on my theoretical model, this is why this is going. Stepwise regression, no theoretical basis, right? I'm just gonna throw a bunch of stuff in. Like, this is all the stuff that I have. I'm just gonna see what turns out, right? And so this is difficult, it starts to become difficult to defend why models are in there, or explain why certain variables are predicting outcome if I don't have any theoretical basis, right? Also, we end up having sort of what variable, right? In this case, variable 1 jumped in there because I had the strongest relation, bivariate relation with my outcome. But maybe the difference between sort of X1 had a correlation of 0.32 and variable X2 had a correlation of 0.31, right? Because of that trivial difference, X1 gets set up as a much more important predictor in the model than X2, when that difference is kind of arbitrary. If we were to resample, that could easily be flipped. Maybe in multiple resamples it would be flipped because maybe in general, X2 is actually has the stronger relation. It was just in this sample, it didn't, right? It happened to be like a half step behind X1. And so what ends up happening is we have a model that is capitalizing on specific characteristics of the sample, and then I have a hard time replicating this down the road because what it did is it capitalized on weird stuff going on in this data set that I have, and no one will ever replicate this effect ever and ever because of how these variables are entered in. And then we have a tendency to overfit the data, right? Based on sort of these 20 variables are all included in this model, and now, but we've done a lot of capitalizing on chance, and now we can say, Lauren says, oh, these 20 variables, this is the best way to predict some outcome. Well, probably not, right? If we were to include those 20 variables down the road, we might find that many of those don't actually end up predicting much of anything. We just kind of overfit in this sample. And so we do have procedures, and this is starting to become an increasing interest or reinterest in psychological science in terms of like machine learning and data mining types of things. Just very important to recognize the conceptual and statistical limitations of some of these models. And this is often, like, I would have strong reservations about a paper that took this approach unless they gave me a really strong rationale for why they were doing it and how this mapped onto onto their research question. People kind of understand what stepwise regression is going through for? All right. Practical stuff, and then I'll let you go. Model selection, just make sure you have good measures. Right? If you don't have good measures, your model's not going to be any good. A lot of times people come in and want having questions about things that are thought to be a statistical issue but aren't. There's not a way to statistically magical up variables and data that's crappy. Right? If you've got garbage data, there's not a statistical fix for that. Right? Like I can't covary something and make it better. It's just going to be a bad variable, right? So this is where the statistics comes in with research planning and sitting down and saying, all right, if this is what I want to look at, what's the best way to measure this within the capacity that I can? Make sure they have good, reliable measures, because if we don't, it's tough to know whether or not our model's no good or our measurement wasn't any good and it's just full of static, right? You're trying to tune in Bon Jovi on your FM radio in the middle of Wyoming and there's no signal there, right? The signal's out there, we just can't pick it up, there's too much static going on, okay? And so again, when we're thinking about putting together our models, we want to get best models, have a small or a sort of discrete collection of predictors maximally associated with our outcome and minimally associated with others. Well, a lot of times when we're doing this, we start particularly secondary data analysis. We're like, well, what if we do this? What if we do this? What if we do this? Starts throwing things in. They're all basically measuring negative affect in the same thing, right? It's not an efficient model. What we want to do, get the best predictive model with the fewest variables. That's a good model to work for. Okay. Other thing, people want to know how many people do I need? What's the sample size that I need? This is a complex question. There's not one answer, right? You see different rules of thumb. Those are generally garbage. The sample size that you need for an adequately powered test depends on how many predictors you have, what your significance level is. More importantly, sort of what the effect is that you're expecting from these individual effects, right? And so we can say, oh, you need X number of predictor or X number of observations per predictor, things along those lines, right? But those rules of thumb start to break down when we have skewed dependent variables, right? We've got small effect sizes, we've got measures that aren't super reliable, right? There's more static going in there. These are all things that start to play in. And so at this stage of the game, right, you've entered psychological science at a point where there really is no excuse for you just running a power analysis, right? Unless you are running a regression model where no one's ever looked at the correlation between X and Y, you should probably have some reasonable idea of the relation between whatever your predictors are and whatever your outcome is. We've got amazing analytic tools where you can just go through and very quickly say, well, for a model with this many predictors, and we're assuming I want to power this to be able to detect effect sizes of about this magnitude, this is the number of people that I would need to have in that model. Now you're probably going to be disappointed with what happens with that because it's probably going to be a lot versus a little, right? You can choose whether or not to say, okay, I'm going to do this or not, but at least you're walking in knowing that, oh, I've got a coin flip chance of detecting any effect that I might have if I get the 80 people I was hoping for, right? So again, would encourage you to shy away from rules of thumb. I used to assign a paper that had rules of thumb, this number of observations per predictor, but I took that away because this is better than what you should be doing anyway. So, all right. I finished, I stopped talking right at 4, so we're about a half hour behind on the break. But questions on basic regression stuff? Okay, cool. Let's take 10 and then we'll jump back in with moderation stuff. All right, folks. Gonna jump into moderation here. I don't know. Candace, I would say moderation probably one of the more technically involved analyses that we'll do, in addition to mixed factor ANOVA, stuff like that at the end, right? Okay. So all the goings on that we had about making predictions and precise interpretations of individual regression coefficients, this starts to become very, very important when you start doing this and being able to go through and double checking your procedures on this. Assume that you'll do this wrong every time you go through and do it, and you'll have to catch your errors and then go back through and fix them. I still do this, right? I'm going to go back, getting too big for my britches, and I'm like, that doesn't make any sense. Now I got to go back to figure out what I did wrong, right? But the nice thing with this is if you understand the process, if you understand what should be going on, there's several fail-safes that you'll be able to go through and check and see whether or not you conducted this correctly. So when we're thinking about our regression models, right, we hit a point where whether or not there's a unique effect of X on Y starts to become kind of boring and not terribly interesting in terms of contributing to the literature. Right, if we go through, like in my work, we know that PTSD holds a relation with social support, right? That's been replicated again and again and again and again and again. Me testing to ask whether or not PTSD is related to social support isn't an interesting question because the answer is yes, it is, right? And so with our basic regression models, sometimes you'll hear about this in terms of a horse race, right? Like if I dump a bunch of things in the hopper, which one of these holds out with a unique relation with my outcome controlling for everything else? But we start to become kind of limited in terms of what we can say about the nature of the relation between X and Y, right? And so if we have strong evidence, and again, this is where a lot of our meta-analyses have really started to become, I think, conceptually and advantageous and helpful from an applied approach. If we have strong evidence that there's a relation between X and Y in the population, one of the things that we can do to start asking more interesting questions, get more into this, is start to ask under what conditions this effect holds, right? So I know that PTSD is related to social support, right? Are there conditions under which PTSD isn't related to social support? Or are there situations in which PTSD is very, very strongly related to social support, and at other points it's not, right? And essentially what we're asking about here is moderation effects, okay? As we touched on last semester, we're looking with moderation at the extent to which some external factor starts to impact or change the nature of the association between X and Y. Okay? So if we're talking about our moderator individually, moderator M, so this is going to be any variable that impacts either the magnitude or the direction of the relation between X and some outcome Y. For example, I might say the impact of stress on physical health depends on the degree of social support available to that individual. Okay? What might I be expecting to go on in this situation here, Katie? What might my hypotheses be about the impact of social support on the relation between stress and physical health? So if I'm saying I'm looking at people with high levels of social support and low levels of social support, what might I hypothesize being the impact of high versus low levels of social support on the relation between stress and health? What do you think? What would high versus low levels of stress or support do for the relation between stress and health? That's kind of getting at some mediation types of stuff. What do you think, Antoine? So what's the impact of support on the relation between stress and health? or yeah, stress and health. How about this? For people without social support, oh, Sam, you got an idea? Run with it.
When you increase social support, do you strengthen the relationship with physical health? Stress and physical health medium.
Perfect. Why is that?
Because the more social support you get, the less stress impacts your physical health.
Yeah, no. That's exactly right. So maybe if I don't have a lot of social support, I have a very strong relation between stress and physical health. But at high levels of social support, those two things much more modestly correlated, maybe not even at all, right? And so again, the thing that's important to think about in terms of moderation is we're looking at how some third variable impacts the relation. How does this impact the association between X and Y, right? So Katie, some of the stuff you were talking about starts to get into mechanisms and things like that, right? And this can be a little bit tricky in terms of your justification. So what's the theoretical or conceptual reason we would expect sort of this outside factor to impact the relation? But again, what we're looking at is we're starting with this base relation. When you're trying to keep this stuff together, think about this scenario where in my literature, X and Y are related. We know X and Y are related. If I were to tell someone in my field that X and Y are related, they would say, yep, I know, so does everybody, right? What we're trying to do with moderation is say, under what conditions does this hold, right? What are third factors that we can go through that are going to start to impact the nature of the relation between X and Y? Okay? Let's say we're looking at the relation between psychological distress and substance use differs across men and women, right? Lauren, what might be a hypothesis we would have here? So what's our base relation? What's our base relation here? What's my X and what's my Y? Okay, psychological stress and substance use, right? I know these things are related with one another, right? And so what I want to know is what the impact of gender or biological sex is on this relation. And so what might be my hypotheses?
Then, as psychological stress increases, okay, I'm getting confused.
So what differences would we see in the association of psychological distress and substance use across men and women? And what do you mean by different levels?
Like higher levels of distress and substance use.
Okay. So again, remember. No. This is hard to get your head around because remember what we're looking at is the impact on the association. So who might you expect to have a stronger relation between psychological distress and substance use, men or women? Okay, right. And so what we might see then is for men, for women, psychological distress has a relation with substance use, right? But if we look at men, it's much stronger, right? And so this is, we're saying, again, with each one of these, the trap here is to start thinking about this in terms of mean differences, like who's has higher levels or lower levels, things along those lines. That's not the point of moderation within at least what we're talking about here. What we're looking at is like, how does this third factor impact, how does this outside factor impact the association between X and Y? Now, sometimes it can make the association between X and Y stronger or weaker. Sometimes you can completely flip it all around, right? At high levels of my moderator, I have a positive relation between X and Y. At low levels of my moderator, I have a negative relation between X and Y, right? And so again, when we're trying to wrap your head around this and think about moderation questions, it's, okay, I know that X and Y are related, or there's a good literature that says X and Y are related. What's what are some additional factors that are going to start to change the nature of this? Because probably it would be safe to say that all effects are moderated by something, right? I don't know that I can identify some relation between two variables that are going to be identical across all situations for all populations at all times, right? And so this is what we're looking for in terms of our moderators.
Is this like an interaction effect?
This is exactly an interaction effect. This is the same thing that we're talking about in our ANOVA models, right? Any interactive effect you have is a moderation effect, right? So men and women differ, or the differences in aggression across men and women is dependent on, I don't know, biological risk factor or something like that. So if men and women both have sort of this gene, then sort of aggression levels are the same. If we don't have that gene, then men and women are different, something along those lines, right? The only thing that we're doing here within a regression framework is we're looking at continuous moderators and not having to break things down into different groups. Okay, so again, if we're looking at a moderation, we're talking about looking at conditions under which some association is strengthened or weakened, right? The focus of our interest here is on the relation, right? Is this relation increased, decreased, or does it change directions based on some level or some other outcome variable? And what we say, if we do find evidence of a moderated effect, right? If we do find an interaction effect here, right? We would say that the relation on X, the relation between X and Y is conditioned on M. So the thing here is, if you ask me, what's the relation with X and Y? I mean, I don't know. Tell me what level of this other thing that we're talking about, or this, give me information on this other variable, because that's going to depend on the relation between X and Y. Because at high levels of this third variable, I would expect a pretty strong relation. At low levels, I don't expect any relation at all, right? And so what we talk about in the presence of moderation or evidence of moderation, we aren't talking any longer about main effects or anything like that. We're talking about conditional effects, because the relation between X and Y is going to be conditioned or dependent upon some level of some other variable. And people have a headspace on what we're talking about and how we're thinking about moderation here. Okay. Now, historically, looking at interactions here with ANOVA models, right? I want to look at the impact of gender and ethnicity on social bonding. Social bonding is a continuous outcome variable. I've grouped people based on gender and ethnicity, right? And what I want to do is see whether or not social bonding differences in men and women in social bonding is in some way dependent on gender, or excuse me, is dependent on ethnicity, right? In some cultural groups, there's not a lot of difference. In other cultural groups, there is quite a difference, right? This would be an interaction effect where we would say the relation between gender and social bonding is conditioned on cultural background, right? And if we were trying to run this in an ANOVA model, we can say, okay, we've got these people we're going to categorize into men and women, and we've got ethnicity that we're going to say is sort of this group, that group, the other group, right? And we're going to look at mean differences here, run this in an ANOVA model. Okay? And this is fine, and this is a great way to run things if we're working with categorical IVs or predictors, right? But what happens is this whole thing starts to break down, at least from the perspective of how we would typically approach and plug things in with ANOVA when we're looking at some sort of continuous IV, right? If I want to look at the impact of ethnicity and SES on salary, right? Is your salary dependent on your ethnicity and whether or not you come from whatever your parents' SES background is, right? All of a sudden this starts to become more difficult because SES is hard to break into a categorical variable, right? Because that occurs along a continuum. What we saw, not in your lifetime necessarily, but at one point, right, the idea was to, well, we've got this continuous variable. And so what we're going to do is we're just going to dichotomize it. We're going to use median splits, right? We're going to say, all right, everybody above this is going to be high, everybody below this is going to be low, and so then we're just going to run this median split in an ANOVA model, and we're back to good, right? But problem here, and again, hopefully you've been reading articles on cost of dichotomization and some of those other things, right? What we do is we lose power and potentially bias effects, right? Because what we've done is we've said everybody from this point and above is high SES, and everybody at this point and below is low SES. And in this model, all these people are identical, and all these people are identical, right? But we know that that's not the case if we actually think about sort of what this construct is and what it's trying to measure, right? And so we start to become very, very limited if we start forcing everything into dichotomous predictors. But what we can do with our regression models, we can start to test our interactive effects across any combination of categorical continuous predictors, assuming that we've coded things correctly, right? Again, ANOVA is just a special case of regression, and we can use this larger general linear model to go through and take a look at interaction effects between continuous variables and continuous variables, or continuous variables and categorical variables, using all information along the continuous scale, right? We don't lose any information with this process, right? So we don't have to go through and look at the relation between X and Y in our sample of men and our sample of women, right? Because if we do that, we just cut our sample in half, right? And so now I don't know if I don't not see a significant relation between X and Y in men because it's not there, or it's because I have half the sample I did with everybody, right? And same thing with our continuous variables. I don't have to dichotomize it. I can use the whole range of information on this continuous variable, and that's going to give me a better estimate of the true nature of the relation and the moderating effect on whatever our outcome is. Okay. Questions about this? Okay. All right. So, conceptual example. Think about moderation, and we're just going to pick up. We're going to assume, or we're going to pretend that our outcome variable for that last example wasn't crap. we're going to ignore the fact that we found evidence of non-normal residuals and pretend that we're good to go with this. Okay. So same variables, but this time maybe our question is do opiates impact or influence the impact of physical pain on role functioning in people who've been exposed to motor vehicle accidents? Okay. So in this situation, Sam, what is my base relation, and what am I conceptualizing as my base relation, and what am I conceptualizing as my moderator in question one?
So opioid medication and impact of
Tell me what's my X, what's my Y, and what's my M?
X would be opioid medication. Y would be physical.
Take another look. Take another look. What's my base relation? Yeah. Right. So my base, I know that physical pain impacts role function, right? If you hurt all the time, you're not going to be functioning. It's right, left, and center, right? Like, is this a good thing? Do we see that if we have people on opiate medications, do we see this impact the nature of the relation between pain and functioning? Because if the medications are working the way they should, what should I see, Alex? Okay, if I'm interested in the extent to which opiate medication, pain medications, are impacting the relation between pain severity and functioning, If the medications are doing what they should be doing, what should I see?
Well, most people should increase.
Okay, not talking about increases and decreases. Opiate use is medication, or opiate uses are moderator, so what am I thinking that this is going to impact?
It's going to impact their relationship.
Exactly, right? And so what should the relation between pain and functioning be for people who are taking opiates versus those who aren't?
They'll be different.
Okay, so they'll be different. Who would we expect a stronger relation between pain and functioning? Would we expect a stronger relation between people who aren't taking medications or who are taking medications, if the medications are doing what they're supposed to be doing?
We would expect that people who are taking appropriate medication, that the relationship will be less strong.
Perfect, right? Because if I'm taking medications, that's making me feel better. My levels of pain might be high, right? But I'm using this to and so I would expect a weaker relation between pain and functioning if the medications are doing if I'm not taking medications, my pain increases, my functioning decreases, right? I've got a stronger relation there than I would if I'm taking medications. Those medications are doing what they're supposed to, right? Okay, what about, and so then also, let's say we're interested, does pain severity change the relationship between PTSD and neural functioning following a motor vehicle accident? Well, what do you think? What's my X and my Y and my M here instead of here?
The relationship between PTSD and neural functioning is based on pain severity.
Right. So here's the relation: PTSD and neural functioning. People who have post-traumatic symptoms aren't doing super well, right? But I also know that people with PTSD also have comorbid pain, particularly after accidents. Does physical pain change the nature of the relation between PTSD and neural function? Right? This is a little tricky. What do you think? What might you hypothesize about this relationship?
I'm having trouble verbalizing it because the pain severity is also it's a continuing.
And so thinking about at high levels of pain severity or low levels of pain severity.
So at higher levels of pain severity, the relationship between PTSD and neural functioning would be stronger
Okay.
than at lower levels.
Okay. So a hypothesis here could be that I'm expecting the relation between pain severity and PTSD, or PTSD and neural functioning to be stronger if we have people with high levels of pain than for people with low levels of pain, right? So what we're getting here is we're getting our interactive effect, right, that we're looking at here, our moderation effect, and then sort of if we were to go through and probe what specifically is going on within this interaction. So again, in this case, we have pain, opiate use, PTSD, role functioning. We're going to pretend that we didn't violate any assumptions, and this is all looking good to go. So these are the same data that we just looked at with the basic regression model. Yeah.
So one of the assumptions of a regression model is that the relationship even, but if we have like a, I guess like a parabolic curve within the relationship, would we still be able to run moderation if we think that we know what's causing it, like what we know what creates like the two separate examples, or is that
Not if we're running a linear model, right? I mean, if we're running a linear regression model, everything has to be linear, right? If we know that X and Y are share a nonlinear relation, that's fine. We can account for that, but we still have to force everything to be linear regardless. And this is one of the things that comes up in logistic regression. We're using a linear model to model something that's by definition not linear, and so we have to jump through some hoops and some gymnastics to get to that point. All right, so going to talk about centering. Centering is incredibly important, although some people would argue that it's less important. I would take a traditional standpoint, argue that it's very important. What we're going to do before we jump into our moderation analyses, and probably before you're running any type of regression analyses, want to consider, what do we center our variables? Okay, What we're doing when we're centering our variables is we're going to go through, we're going to rescale all of our independent variables. We're not centering our dependent variable, not centering an outcome, right? Do not center your outcome, circle it in red, okay? If we're looking at our independent variables, what we might want to do is go through and take all our predictors, rescale it so that the mean of all of our predictors is 0, okay? And we do this by taking each of our scores and subtracting the mean. Okay. So if I'm an SPSS, I'm going to say centered PTSD is equal to PTSD minus whatever the mean value is for PTSD. And what this is going to do is it's going to set the mean of that variable equal to 0. It's not going to change the standard deviation though. So it's different than standardizing, right? If we standardize, we create z-scores, then the mean is 0 and the standard deviation is 1. If we center, it changes the mean value to 0, but the standard deviation remains the same. That doesn't change at all. Okay? So we're just rescaling this down. So here is our uncentered variable, right? We got some variable ranging from 0 to something up there, right? And our mean of this distribution, 5.6, standard deviation of 2.3. Say we've got a perfect, lovely, continuous variable because we've got 1 million people in this sample, follows a nice curve. It's a continuous variable, and so here's our mean value, right? So, person down here is 0, right? Well, and so in our raw distribution, our raw scale, 0 is down here at the end. Okay. What we do though, if we take every value in our set, right? If we say SPSS, create a new variable called centered, whatever this is, equals to variable name minus 5.6. What ends up going to happen is we're going to get the exact same distribution, but now this, everybody who was at 5.6 is now at 0. Okay, this person who was 0 is now down here, some negative number, but the mean of the distribution is 0. Standard deviation is still 2.3, right? These aren't z-scores. We've just taken this distribution and changed what is often an arbitrary scale anyway, and just shifted it down. So 0 represents the mean value of this variable. Okay. People see what we're doing here? So again, this person and this person, right? So this person that was 5.6 is now 0. This person that's 0 is now negative, well, I can do negative 5.6, what their score would be on account of math, right? But what ends up happening here is we end up having more interpretable models. Remember that when we're interpreting our individual coefficients, right? This is the relation between x and y with all of their predictors held equal to 0, right? Now, from an interpretive standpoint, what's the problem with holding all other variables equal to 0? Mathematically, it's fine, and that's what's going on. From an interpretive standpoint, what could be problematic with all other variables set equal to 0? What's that?
Are you asking if we have it centered?
No, if we don't have it centered. What about in that PTSD and pain model? Do we have a lot of people with PTSD equals 0? Do we have a lot of people with pain equals 0? Right? So basically we're saying this is the relation between x and y for people who are not representative of the sample, right? What happens if 0 is not a real value? What if our scale runs from 1 to 10? Then we're saying this is the relation of x and y when all of our variables are held at 0, but I don't know what 0 means for this variable because 0 is not an actual scale, right? And so we end up with our raw variables, we're making interpretations on things that actually, I mean, mathematically it's fine, it doesn't change the nature of the relationships at all, but it's just not all that conceptually meaningful, right? Angela, what happens if I center those variables? Now what's my interpretation? Exactly, right? This is a relation between x and y. Interpretation is still, this is a relation between x and y with all of the variables held constant at the mean. But or excuse me, with all of the variables held constant at 0. It's just now with our centered variable, all of the variables held constant at 0 just means all of the variables held constant at the mean, right? So it doesn't change our interpretation. Our literal interpretation is the same. It's just 0 is now a meaningful point on the scale as opposed to something that may be sort of on the very low end where no one is actually falling, or at some value that's not even a real value on the scale, right? This is the relation between diet and between calories consumed and weight with height held equal at 0. Well, height's never 0, right? But if I center height to be equal to the mean, this is the relation between calorie intake and weight with height held constant at the mean of the sample. So it helps us with interpretation. It helps us calculate our interactive effects, right? Having 0 in the mix is nice, because when things are held equal to 0, what happens to them if we're particularly multiplying anything? They disappear and go away, right? And also starts to address our collinearity with our interaction terms, right? Because what we're going to do, if I say I'm looking at the relation between x1, or the impact of x1, x2, and the interaction of x1 and x2 on my outcome, if I create a product term of x1 and x2, what can happen is I can start to get x1 and x2 start to be very, very highly correlated with the product term. Our centering starts to address those things. So for these reasons, not just for our moderation models, but for any regression analyses that you would run, wanting to consider centering those variables, because it's often, at the very least, it ends up being helpful with interpretation stuff. Questions on centering or what that looks like, why we would do it? So what happens when we center variables? Nothing bad happens. If we rescale by an additive constant, right, we're just subtracting the mean from every score in the distribution. No impact on the shape or variability of the distribution. It looks exactly the same. Your histograms are going to be exactly the same. It's just the center variable is, or the center value is going to be 0. Doesn't impact correlations or regression coefficients if our models don't contain interactive effects, right? So if I look at the correlation between x1 and x2, and then I look at the correlation between centered x1 and centered x2, it's going to be identical, right? If I want to look at the best linear combination of x1, 2, and 3 on my outcome, and then I look at the best linear combination of centered x1, 2, and 3 on my outcome, those regression coefficients for each one of those predictors is going to be identical, as long as there's no interaction terms in there, okay? My constant's going to change, right? Because again, this is the predicted value of my outcome when all of the variables are held constant at 0, right? It's a predicted value when everything is really low, or when everything is expected to be held constant at the mean, right? And so your regression constant is going to change, your intercept is going to change, but your actual regression coefficients for your individual predictors is going to be identical, okay? Centering will change the coefficients you see in models that have interaction terms in them, except for the highest order term. And so I have a regression model that has x1, x2, x3, and then I've got 2 interaction terms. Okay? My interaction terms in my centered model and my uncentered model are going to be identical, but my lower order terms, my sort of main effects or my conditional effects, will start to shift around. If I go through and include a 3-way interaction in there, my 3-way interaction, the coefficients for my 3-way interaction will be the same in my centered and my uncentered models, but my 2-way interactions will be different, as will my first order effects, right? So centering will alter your regression coefficients, except for the highest order term. This is important. This is a good way to go through and check to make sure that what you've done is consistent. You've done things right. If the interaction terms for prior order interactions start changing around across models, you've got a problem in there somewhere. Okay. Simple slopes for multiplicative effects, we'll talk about those, are not affected, and the shape of the simple slopes isn't going to change as a consequence of centering. All of that stuff is going to remain the same. We'll talk about what some of these things are when we start to run through our models here. So for our conceptual example here, in our MBA sample, right, our regression that we ran, we've got our role functioning variable, and our linear function here is our intercept, coefficient for pain, opiate use, and PTSD. So my centered solution, pain and PTSD centered at their respective means. Opiate use is a dichotomous indicator, and so if I center that, it's just going to mean that non-use is negative 0.5, use equals 0.5. As long as this is a balanced design. This is not on your slide, I changed this before I came up. Note that just because you center a dichotomous variable doesn't mean values are negative 1 or 0.5 and negative 0.5. That only happens if you have a balanced design. If you don't, if you have an unbalanced design, again, we're taking whatever our 0, 1 variable is and subtracting the mean, and so your values for your dichotomous indicators can be different. But if you've got a balanced design, it should be something that's close to negative 0.5 and 0.5. Okay. So if we do this, right, if we regress role functioning onto our centered coefficients, this is the model that we get. Okay. Intercept of 48.2, coefficient for pain, opiate use, and PTSD. Okay. Morgan, tell me what, give me an interpretation of this coefficient here.
So when x is 0, y will be 48.2.
Elaborate that on.
Holding all others constant.
Well, for this, we've got several x's in here.
Yeah.
So how would we interpret that coefficient?
Forget already.
So which one of these are we going to hold constant at 0? This one, and these ones can be whatever they want?
No,
All of them, right? And if we're holding all of them constant at the mean, I'm holding all of them constant at 0 in the centered solution, what does that mean? All right, so holding each one of these variables constant at the mean, we would expect our outcome to be 48, okay? Now this starts to get a little bit tricky, because what does it mean to hold opiate use constant at the mean? That's a dichotomous variable, right? Basically what you're saying is you're just saying controlling for that variable, right? So taking opiate use out of the mix, controlling for opiate use, so saying holding pain and PTSD constant at the mean and sort of controlling for opiate use, right? I mean, you don't have to get that elaborate. You can just say holding all variables constant at the mean. I'll kind of know what you're talking about here. But conceptually what you're saying is that we're holding pain and PTSD constant at the mean and kind of controlling for shared variability with opiate use here. Katie, how would we interpret this coefficient for pain here? Role functioning, so decreasing role functioning, holding
all others constant.
perfect, right? So again, interpretation is this exact same, it's just now 0 is a meaningful point, right? 0 just means the mean of our variables, right? So it doesn't change things all along. You could actually say, you could give me the exact same interpretation. You say, so the relation, we would expect a per unit increase in pain, we would expect a 10.7 decrease in role functioning, holding all of the variables constant at 0, right? Well, that's true, but the interpretation implication there is holding all of the, well, opiate use is a little bit tricky. We won't worry about that right now, but same thing for PTSD here. Okay. So people seeing the interpretive value of centering and kind of what this is doing in terms of making our interpretations, our literal interpretations of our coefficients, so that they're not nonsensical. Okay, so if we're looking at, and so this is an additive model, right? We don't have any interactions in this model here. If we go through and we take a look at our uncentered solution or our centered solution, our R squared, identical across here, right? Our adjusted R squared, identical. Our standard error of our estimate, the same, right? If we go down through and we take a look at coefficients for opiate use, pain, PTSD, standardized coefficients, significance values, part and partial correlations, all of these are identical. Only thing that changes is this constant, right? Because what we're talking about here is, if we think about this is the expected value of role functioning when, for people who aren't on opiates, who have no pain and who have no PTSD, right? Those people are functioning higher than people who, the expected value of role functioning for people who, at average levels of pain and average levels of PTSD, controlling for opiate use. Okay? And so we see a shift in our constant, but our coefficients are going to be all identical. Questions about this? Kind of seeing that as really centering our variables has really no impact on our base regression model outside of just changing that constant value a little bit. Okay. All right. So again, think about that for our moderation effects, right? What we're trying to look at is what is the impact of opiate use on functioning at different levels of pain and PTSD. Okay. So the base rate is opiate use or pain and PTSD. What if we start changing different levels of opiate use? Are we looking at people with opiate use, without opiate use, right? And so what we can do with our additive model, we can actually just start plugging values in and see what happens, right? So we say here, right, let's see what's the nature of the relationship between opiate use here and outcome if I'm looking at people with high pain and high PTSD. So I take my regression equation, run it out, intercept my slope for pain, and here's going to be a high level of pain, right? Because I've centered pain, and I'm setting high levels of pain. I'm conceptualizing high levels of pain as one standard deviation of the mean, okay? So I'm setting this value of 1.34 that's corresponding to high levels of pain. This is my relation of opiate use, which is what I'm interested in, and then high levels of PTSD, because the standard deviation unit above the mean, standard deviation of PTSD is 19.7, right? And so I'm just going to plug 19.7 here. So basically, this is one standard deviation above the mean, right? So what I want to know is what's the relation between opiate use and role functioning at high pain and high PTSD. Well, we go down through and we run the math, reduces it down to this equation, right? And so for people without opiates, it's going to be negative 0.5. For people with opiates, 0.5. This is what we get. Right? What's the difference between that number and that number, Sam?
No opioid is higher than.
Okay. Well, what's the difference between these two numbers? Yeah, it is 0.69. That's a coefficient, right? So we get a 0.69 difference between people with and without it. So if we're looking at people with high pain and high PTSD, we get a 0.69 difference, right? What happens if we want to look, well, we're going to switch things up. What about people who are low in pain and high in PTSD? Right? We go through, we say, all right, here's my equation. I say, well, now I've got low pain, so we get standard deviation to low, right? So again, my standard deviation of pain is negative 1.3, so I got negative 1.3. High PTSD, 19.76, plug that in, run that out, right? This is my equation. So we get no opiate use, high opiate, or no opiate use, opiate use. What's the difference between these two numbers? 0.69, right? It doesn't matter. I can throw whatever numbers I want to for pain and PTSD, right? It doesn't change the nature of the relation between opiate use and PTSD, or opiate use and functioning, because it's going to be the same across each. It doesn't matter what values. This is constant, right? This is a constant relation. Same thing, what if I want to look at the relation of PTSD functioning at different levels of opiate use? Right? Again, my equation, low pain and opiate use. So I got low pain, standard deviation below. Opiate use corresponds to a value of 0.5 in the data set. Here's my relation with PTSD. Run this out. Relation between PTSD and outcome is negative 0.23, right? Same thing, high pain and no opiate use. How does this impact the relation with PTSD and my outcome? Plug these other variables in. High pain, no opiate use. What does that impact on the relation with PTSD? It doesn't. It's still the same, right? My intercept is different, right? So I'm expecting higher levels of role functioning at low levels of pain than at high levels of pain, right? But it doesn't change the impact. The nature of the relation between PTSD and role functioning stays identical no matter what values we plug into this. Okay? And this is the issue with our additive models. In our additive models, the slope of the relation for any one of our coefficients is going to be identical across all other predictors. Okay? The effect of x on y is constant for all values of x. And so this is why I said, when I'm telling you, say, okay, Angeline, but add that, so this is when in our regression model, this is the relation between x and y with all other variables held constant at 0 or all other variables held constant at the mean. It's a little superfluous because it doesn't matter what we hold those other values constant at, right? We can put them at whatever we want. The nature of this additive model, the relation between x and y is always going to be the same, right? It doesn't matter. I mean, technically, when we're saying all other variables held constant at 0, we're just saying that this is a relation between x and y, the unique relation between x and y if we control for all of the variables in the model. But it actually doesn't change the nature of the relation if we start throwing other values in there, because we're estimating this model, it's going to be the same no matter what. Okay? And if we were to plot this out, I mean, our intercept changes, right? But the nature of the relation between role functioning and PTSD in this additive model is going to be identical no matter what values for these other predictors that we throw in here. Okay? And so this is why we can't test moderation models in our standard additive regression, because it doesn't matter what values of the other predictor we have. I can throw different stuff in there, but the relation between x and y is going to be identical across all other values of our other predictors, unless we start putting in interaction terms. And this is where we start to get into moderation and testing whether or not we have evidence of reliable interaction terms, where we can say, yeah, it looks like the nature of the relation between x and y starts to change depending on what other values we're at, right? But even if that's the case, we don't know it unless we put those interaction effects in there, okay? So opiate use might impact the nature of the relation between PTSD and role functioning, but unless we actually model that interaction, we'll never know, because maybe that relation is going to be constant. Okay. All right, questions on any of this? This is a good stopping point.